All right, so in this video, what I'm going to do is I'm going to extend the idea of SOHCAHTOA to the unit circle. All right, so I'll tell you what a unit circle is in a few minutes, but before that, I want to talk about what are called special. Whoa, that is crazy. Hold on a second. I want to tell you about what are called special right triangles. So there are two special right triangles. And the reason that they're called special right triangles is that you can find the side lengths without using the Pythagorean theorem or SOHCAHTOA. All right, so for example, this one on the left here is called an isosceles right triangle because these two angles here are both 45 degrees. So since the angles are equal, that means that both of the legs are equal, and then you have the hypotenuse. And what's cool about that is there's a little like formula or, kind of thing that you can memorize in order to get a missing side if you're given one of them. So for example, if you're given that this leg has a length of A, then this leg would also have a length of A because they're equal. And without doing like I said, the Pythagorean theorem or like any SOHCAHTOA, you can actually get the hypotenuse by taking whatever the leg is, which is A, and multiplying it by the square root of 2. So for example, if you have a isosceles right triangle, so I'll just try to draw one here, okay? And obviously this would have to be marked 45 degrees for you to know. And let's say that this leg right here is 3. Well, what you know then by this formula up here is that the other leg is 3, and then the hypotenuse is just 3 times the square root of 2. So like hardly any math involved there. You can kind of just use the little trick, okay? Now, it gets a little bit more confusing though if they give you the hypotenuse and you have to go backwards. So let's say, for example, that this hypotenuse was 7 and they wanted you to find the legs. Well, from the leg to the hypotenuse, which I'll write over here. So if you want to go from the leg to the hypotenuse, you take the leg and you multiply by the square root of 2, and that gives you the hypotenuse. Well, if you want to go backwards, so if you want to go from the hypotenuse, all right, let me spell that correctly. If you want to go from the hypotenuse to the leg, you would take the hypotenuse, I'm going to abbreviate it, and divide by the square root of 2, and that would give you the leg. So if we take 7 and we divide by the square root of 2, we have to rationalize it. And so for the legs, we're going to get 7 root 2 over 2. So this leg right here would be 7 root 2 over 2, and then this leg would also be 7 root 2 over 2. Okay, so that's called a 45, 45, 90. Now the other type of special right triangle is a 30, 60, 90. And that one's a little bit more difficult to think about because none of the legs are equal. So we actually call the side opposite the 30-degree angle the short leg. And the short leg is always given the letter B. To go from the short leg to the long leg, so this side right here is the long leg, you take the short leg, which is B, and you multiply it by root 3. And then to get the hypotenuse, you take the short leg, which is B, and you multiply it by 2. So those are the formulas right there. The short leg we call B. The long leg we call B root 3. And the hypotenuse we call it 2B. So I'll try to draw an example over here. And I'll just pick a number for one of the sides. And then we'll get the other one. So here's a 30, 60, 90. And so I'm going to call the long leg, we'll call it 4. Okay? Now, the long leg is b times the square root of 3. So if we want the short leg, that's just b. So to go from the long leg, let me move this down a little bit. To go from the long leg to the short leg, we want to go from b root 3 to b. So we would divide by the square root of 3. So we take the long leg and we divide by the square root of 3. Think about it. We want to make it smaller, right? Because it's the short leg. And so we would rationalize this by multiplying the top and bottom by root 3, and we get 4 root 3 over 3. So the short leg is 4 root 3 over 3. Okay? Now, we go back to our picture. To go from the short leg to the hypotenuse, you just multiply the short leg by 2. So we would take 2 over 1 times 4 root 3 over 3, and we just multiply straight across the top, straight across the bottom, and the hypotenuse would be 4 times 2 is 8 times root 3 over 3, and that would be the hypotenuse. Okay, so the next thing that you should try after you watch this video is you should try the worksheet on special right triangles. And when you're done with that, you can go ahead and send it to me and I will check it for you. Okay, so try your best on that. If you have any questions, let me know. The 45, 45, 90 should be pretty straightforward. The 30, 60, 90 is a little bit more difficult. The hint that I could give you on the 30, 60, 90 is no matter what side they give you, go back to the short leg first. So like if they give you the hypotenuse, go back to the short leg by dividing by 2, and then it's easy to get the long leg. So on a 45, 45, 90, you only have like one move to make. You either multiply by root 2 or you divide by root 2. But on the 30, 60, 90, no matter what they give you, just go back to the short leg first. I guess the other thing I should show you is sometimes on the 30, 60, 90, or I guess even a 45, 45, 90, you might have to multiply radicals together. So let me show you how to do that. If you have root 3 times root 2, that's just root 6. If you have something like 4 root 3 times 5 root 2, you multiply these numbers on the outside together to get 20, and then you multiply the roots together. So root 3 times root 2 is root 6. Okay? Anytime you have, like, say, for example, root 3 times root 3, that's going to be root 9, which is 3. So sometimes the radical will disappear, but that's just because what you multiply together gives you a perfect square, and then you can take the square root of it. Okay? So good luck on this section, and then what we'll do next is I'll show you how to create the unit circle from special right triangles.